Okay, so Unit 2 is going to deal with a lot of the same kind of motion that we talked about in Unit 1, but it's going to look at it from a different point of view. In Unit 1, we looked at motions in terms of the movement of the object, its velocity, its acceleration, its displacement, that kind of stuff. And while that stuff is important and it'll still be part of what we're doing, now we're going to look at that motion from the point of view of what is causing that motion to happen. What are the forces that are acting on that object? Where is the energy and work coming from to exert those forces and make that movement happen? Okay, so this unit is going to be all about pushing and shoving, okay, and pulling and that kind of stuff, because it's all about the forces involved. So the best place to start is with the most basic physical law. Okay? And that is Newton's first law. Okay? Newton's first law is the most common sense law you can imagine. Okay? We can sum it up in one word, and that word is inertia. Okay? What Newton's first law says is this desk will sit right here as long as nobody touches it. Well, duh. Of course it's going to sit here if nobody bothers it, okay? I mean, if there's an earthquake, it'll move, but that's somebody bothering it, okay? Newton's first law is the law of inertia. And inertia is the tendency of an object to continue doing what it's already doing in the absence of any unbalanced forces. Okay? So this desk has several forces that are acting on it, but it doesn't move because all those forces are balanced. Okay? Now you're probably looking at that desk and going, several? Where is Coder getting these other forces from? Okay? I mean, the obvious force that's acting on the desk right now would be gravity. Because gravity's acting on everything. It's always holding us back. Stupid gravity. Okay? So, if gravity's pulling the desk down, why doesn't the desk fall? The floor. Yeah. Okay? This is actually Newton's third law, but Newton's third law says every action has an equal and opposite reaction. So when gravity pulls the desk into the floor has to push back with an equal but oppositely directed force. Those forces are balanced, so the desk doesn't move. Okay? There's no other forces acting on it. Now, if somebody comes along and pushes the desk, then it will move. But that's because that force isn't balanced. There's nothing to offset that force. Okay? So everyone kind of follow me there. So that's the first situation in which Newton's first law applies to a stationary object. Okay? The object will continue to be stationary as long as there are no unbalanced forces. Now, the second situation is every astronaut's nightmare. An object will continue to travel at a constant velocity unless acted upon by an external unbalanced force. Okay? So what that means for an astronaut is if you become separated from your spacecraft and you have no way to exert a force, you will float away into oblivion because you have no way to change your velocity. Okay? This is why astronauts are either tethered to their spacecraft or have some sort of propellant unit on them. Okay? Like it's a jetpack per se, but it's these little maneuvering jets that are on their spacecraft, okay, that allow them to turn and spin. They're called reaction control thrusters, and they use Newton's third law to move the astronaut around. If those run out of fuel, then you'll just keep doing whatever you were doing when they ran out of fuel. Because in space, no one can hear you scream, and there's nothing to work against. Okay? Like on Earth, I mean, flapping your arms on Earth doesn't do much in the air. It does a little bit. It does a heck of a lot more than it does if you do that in space. In space, you just look panicked. because you are. And you're doing nothing. Space is a vacuum. There's nothing to push against. You can flail all you want. It's not going to make any difference. Okay? Everyone kind of follow me there. That's why that's every astronaut's worst nightmare. If you become separated from your spacecraft, you can't do anything about it. Your only hope is someone else can rescue you. This is what happened to Mark Watney at the end of The Martian. Right? He shot himself up in the air, okay, on that on the little MAV vehicle, okay, and then he exited the spacecraft, and he's like, well, I'll just wave at you as you go by because I can't do anything anymore. I don't have a jetpack. I don't have my spacecraft. It's out of fuel. They have no ability to change my velocity. And then he went Iron Man and cut a slit in his glove, which is one of those things that's like not so great movie physics. Theoretically, that works, but the captain did mention to him, you'd be using an acceleration vector you can barely control. Okay? You cut the slit in your glove and the air starts to escape, you go in the opposite direction of whatever way your hand is facing. So he cut that and closed his fist, and then right away he started spinning all over the place. Okay? Now he managed to somehow get that under control and point his hand in the opposite direction, okay, and kind of get going that way. It works. He found a way to exert a force that he didn't have before. Had he not thought of that, he would have just kept floating away. Okay? I mean, Mars's gravity might have eventually brought him back, but it would have been a long time. Okay? Like he'd have been long dead before he burnt up in the atmosphere. Suddenly being an astronaut is not as cool as he thought it was. Lots of ways space can kill you. It's very scary. Okay? All right, does everyone kind of understand what I'm talking about there? Okay, so that's basically inertia, right? Now, it's Newton's first law that basically a lot of the safety devices in your car are designed around. If you don't wear your seatbelt in a crash, what happens to you? You fly forwards, possibly being ejected from the vehicle. Okay? Why do you do that? Because of Newton's first law. An object in motion will remain in motion unless acted upon by an unbalanced force. Your seatbelt is supposed to be that unbalanced force. If you're not wearing it, the windshield, the road, and hopefully not, but possibly other vehicles will be the unbalanced force. They are much less safe than the seatbelt. Okay? The seatbelt is designed to exert a force on you that keeps you in the car. Okay? Does everyone understand what I'm saying there? I mean, you've all slammed on the brakes and everything in the back seat goes flying forward. It's the same idea. Okay? That's Newton's first law. Those objects were in motion. They were traveling at 60 kilometers an hour with the car. Suddenly the car stops. There's nothing to keep them in place. So they just keep going at 60 kilometers an hour. Okay? I mean, it's actually dangerous to have loose objects in your car. If you stop suddenly, those loose objects can kill you. Okay? Like this is why, how many people have pets? Okay? Do you buckle your pet in the car? Do you have a seatbelt for the pet? If you don't, you should. Not just for their safety, obviously you love your pet, they should be safe too. But it's also for your safety. People are killed by their pets in crashes. If your pet is not secured, they'll fly around inside the car. And if they hit you, they can kill you. Okay? You don't want to have loose objects in the car because Newton's first law, you can't stop Newton's first law. It just happens. Okay? Everyone following what I said? I'm not trying to scare you, but this is why physics is so important. Okay? It's the thing that can keep us safe because it can be dangerous. Okay? We have to use it to keep ourselves safe from ourselves, okay, or from physics, because it can work for or against us. Okay? Now, what are some things that could affect your inertia? Your inertia is the tendency of an object in motion to remain in motion, or an object that is stationary to remain stationary. What are some things that could affect their ability to do that?
Friction.
Okay, friction is usually an unbalanced force, but I know what you're thinking, this desk, if I try to move it, okay, and it doesn't move, I'm pushing on it right now, but it still doesn't move, that's because the forces are all balanced. Friction's there. Friction's acting against me. this desk doesn't move until I overcome friction, and now my force isn't balanced anymore. So, okay, friction could be part of it. What else? Okay, imagine this situation. I'm stuck in the middle of the street. On my left is a child on a tricycle moving at 30 kilometers an hour. Don't ask me how they got, don't ask me how they got going that fast, okay? They're going that fast. On my right is a bus moving at 30 kilometers per hour. And I have to step in front of one of them. I can't stand where I am, okay? I have to step in front of one of them. Which one are you gonna step in front of? The child. You see the bus, then please talk to me after class, okay? All right, so I step in front of the child. Why?
It has a lower mass.
It has less mass. Your inertia is affected by your mass. Okay? What's the most important safety feature in your vehicle? Nope. Nope. Mass. Mass is the most important safety feature of your vehicle. Some have it, some don't. That's why I drive a truck. Okay? I want to win. Hey, in every accident, there's a winner and a loser, be sure. Okay? In every accident, there's a winner and a loser, and the winner is always the bigger vehicle. Always. Mass is the most important safety feature you can have. Okay? Now, I'm not saying you need to go out and buy like 50 cinder blocks and throw them in the back of your Honda Civic. That's not going to work. Okay? Yes, it will change the mass of the car, but you won't be able to drive it because the back end will be dragging. Okay? But mass is important because it affects your inertia. The more mass you have, the greater your tendency to continue doing what you were already doing. Okay? Everyone follow me there? Okay? The bigger you are, the harder you are to stop. And it has nothing to do with how, well, a bit to do with how fast you're going. But if I have two equally speedy objects, okay, and one's lighter than the other, I got a better chance of stopping the light one than I do the heavy one, simply because it has less inertia. I have, I can change its inertia, whereas the other one, I'll change its inertia, but not very much. Okay, I'll become part of it. Okay, so that's something we have to consider. Okay, that's why typically smaller vehicles end up far worse off in a crash than a large vehicle. Okay? Mass matters. I mean, a semi-truck and a smart car collide, there's an obvious winner and an obvious loser there. Okay? The smart car simply doesn't have the mass to deal with that kind of an impact. Okay? All right. What are some other things that we put in cars that help keep us safe? People mentioned seatbelts, airbags. Why do those keep us safe?
Because they balance a forward force. Like when someone's about to fly forward, they push them back, neutralizing the speed.
Right. The seatbelt is simply a restraint. Okay? It keeps you in the car. It foils Newton's first law. It also has a small part to play in Newton's second law. Okay? Newton's second law says that the force that you experience is related to your mass and your acceleration. Okay? So a lot of the safety features in your car are designed to make this number smaller. Because if that number is smaller, this number will be smaller too. And that means you have less force acting on your body. Okay? So your seatbelt, I mean, if you've been in a car accident, like a significant one, you know you get that seatbelt shaped bruise right across your chest. Okay? Like it literally is, it's a rectangle. It's perfectly shaped like the seatbelt. Okay, if you get in a good crash. So it's keeping you in the car, but seatbelts are also a little bit elastic. They stretch just a little bit. You get in a crash more than 50 kilometers an hour and your car's not a write-off, then they'll have to replace the seatbelts because they'll stretch. Okay? They're designed to do that. Okay? An airbag, similarly, is designed to slow your head slowly. Okay? Back in the day, before airbags, lots of people had the same scar. Right across here. okay? Because in an accident, pre-airbags, okay, steering wheels were these hard, inflexible circles that you use to direct your car. In an accident, your head would go forward and hit the top of it and peel your scalp back. Okay? Like, I kid you not, like literally peel it right back. Because they were hard, they didn't collapse. Okay? Before airbags, slightly before airbags, came the collapsible steering wheel, okay? Which was a big safety advancement, because hitting a hard steering wheel not only peels back your scalp, but gives you a bad concussion as well. Because your head stops suddenly and your brain keeps going forward according to Newton's first law. That's why you get a concussion, incidentally. Okay? Your head stops rapidly, your brain keeps moving and smashes into the inside of your skull and gets a bruise. That's a concussion. Okay? So that was bad, so they made collapsible steering wheels. Okay? So if you hit your head on the steering wheel would just cave in. Okay? You could actually cave it in with your fist if you were having road rage. You can, boom, and you had the cool shaped steering wheel after that. Okay? But yeah, they're designed to do that. Now, it's not just the steering wheel. The steering wheel doesn't really have to collapse anymore because you never get to it. You hit the airbag, and most steering columns are also collapsible. If you hit them really hard in an accident, the connecting rod that connects the steering wheel to the axle just breaks. Okay? It breaks, these pins break, and it just goes forward, and you go with it, okay? And it slows you down far more gradually than hitting a rigid object.
So where does the airbag actually come out from?
The steering wheel. If you're in the driver's seat. If you're in the passenger seat, it's usually right above the glove box on the dash. And then you've got your side curtain airbags, okay, all these things that come from like the roof line, from the column panels, okay, all of that. Because people were getting injured in a crash because it's not just forward. Like, we get this idea a crash is always about hitting something head on. But lots of crashes aren't head on, lots of crashes from the side. Okay? And so you need that cushion. If you don't get that cushion from the side, your head hits the window or the door frame or something like that, and you still get a concussion and a head injury, neck injury, stuff like that. Your airbags are designed around this formula that we're familiar with. Okay? The longer a crash takes, the smaller the acceleration. Airbags, okay, anything that collapses away from you, and all the crumple zones on your car are all designed to make the crash take longer. Okay? So the more your car can change shape, the safer it is. Cars are designed to be destroyed in a crash. That will save your life. Old cars, they were designed like tanks. Okay? You hit on a tree head on, you take the ball peen hammer and pound that out. Okay? And that was it, that was done. Of course, you didn't live because, you know, there was nothing inside the car to save you, right? But now we have all these things that are designed around making t bigger. Because if I divide by a bigger number, a is smaller. Okay? So all of these things are designed to make the crash take longer. If your car can crumple, okay, it comes to a stop more slowly than if it just hits something rigid and stops. Okay? That's going to kill you. That's hard. Okay? But something that crumples and changes shape takes a little longer. You hit the airbag, you slow down gradually. Okay? Now, has anyone ever hit an airbag? Had an airbag go off in the face? It doesn't feel nice. It's not a pillow. It feels like a punch in the face, but it's way better. It's way better than hitting the steering wheel. Okay? Because it's an explosion. Right? And what detonates, it's a detonation. The airbag, there's a reaction in there that fills it with gas very, very rapidly, okay, and allows you to slow down better than hitting the steering wheel. Okay? All right, everybody follow me there? Okay. So that's what we're looking at with Newton's first law, okay, and inertia and all that kind of stuff. If there's an external unbalanced force, it will cause you to slow down. If there aren't, then you just keep doing what you were already doing. So I'm going to show you a video clip here. Got lots of those today. It's just one of those days. Thank you. All right, so force is a common word, and it usually means a push or a pull. There's different kinds of forces. There's contact forces. Okay, so if I'm pushing a stalled car, that's a contact force. I'm directly applying a forward force. Okay, using a rope is still a contact force. I'm not directly connected to the object, I'm indirectly connected to it, and I'm pulling on, still a contact force. Friction is a contact force. Okay, stuff like that. Gravity is not a contact force. Gravity is a field force. Okay? It can act on me even if I'm not touching the Earth's surface, right? Which is good, because if it didn't work that way, as soon as you jumped, you'd float away. Okay? That'd be bad. So, gravity, electricity, and magnetism are all field forces. They can act without actually being in physical contact with the object and pull on it. Everybody follow me there? Okay, so you could have a pulling force, like a tow truck, okay? And force is a vector quantity as well, right? This force is directed at an angle above the horizontal, okay? This would be the forces involved in making projectile motion happen. Gravity, pulling directly down on the object, causes it to go through that arc. Okay, a bulldozer tipping something over, pushing dirt. Okay, it's a direct contact force where the object is exerting the force directly on the object. Okay, so we use arrows to identify forces because they are a vector quantity, just like displacement, velocity, and acceleration. Okay, now mass. As we said, mass is directly related to inertia. In fact, it's the measure of inertia. The more mass you have, the more inertia you have, because the greater your tendency to continue doing whatever it was you were doing before. Okay? So, you ever see, like, how many people like watch or play football? Okay. The linemen, okay? The ones who protect the quarterback. You ever see a skinny one? Yeah, oddly enough, sometimes you do, but are most of them like the biggest guys on the team? Why? They're harder to move. You ever see a skinny sumo wrestler? Why? They'd be too easy to move. Okay? You as a sumo wrestler, you want to have a lot of inertia, right? I mean, sumo wrestling is just about pushing the other guy out of the ring. Okay? Well, it's harder to do if you're really big. That's why all the sumo wrestlers are really, really big. Okay, it's harder to move them because they have more inertia. Okay, comes back to that smart car semitruck situation. Okay, the more mass you have, the more likely you are to keep doing what you are already doing. Okay, it's why I can't just walk up to a train and go, all right, you got to move. Okay, and push on it. It's got way too much inertia for that to work. Okay, it's just too big. Now, there's also the fact that that would be on Earth, and gravity and friction and all of that would be working. Okay. If I had that big train out in space, could I move it by pushing it? Yep, absolutely. Okay? And in space, yeah, astronauts are able to do that. All they have to be mindful of is the reactive force that comes back on them. Okay? So if I've got that big train and I push on it in space, yes, the train will accelerate. It will move away from me. And I will move away from it, because when I push on it, it pushes back on me, and I'm way less massive than it is. So my acceleration the other way will be much greater because of my smaller mass.
So if you're in space and you like throw something, would that also push you back?
Absolutely, which is why if you're an astronaut, if you become an astronaut, never do an EVA without taking a big heavy wrench with you. Because if you ever get separated from the spacecraft, with the wrench, you would have a way to exert a force to possibly get you moving. Okay? If I take the wrench and I push it, I push on the wrench, and the wrench pushes back. Now, is that going to be a big acceleration? Nope, but it might be enough. Okay? If you were stationary and you just needed to get moving, that would get you moving. Not very fast, but there's also nothing to slow you down anymore either. Okay? So you'll accelerate for as long as you're pushing on the wrench. As soon as you let go of the wrench, the force of the wrench is gone because you're not pushing on the wrench isn't pushing on you anymore. But at least you get that little bit of acceleration, however small, okay, to get you moving. Nothing's going to stop that velocity now until you run into something.
Would there be a change in force if you were pushing at it slower rather than faster?
Not really. I mean, you could exert a greater force by pushing really hard, but in the end, you can only get so much out of it.
In this hypothetical situation, would there be a difference between throwing it like that and throwing it like that?
Absolutely. I would want to throw it like I demonstrated, kind of like a chest pass, because I want to do it from my center of mass. That way I control the direction of the force. If I put it over my shoulder like this and throw it, it's going to cause me to turn end over end. because there'll be a directed force on my extremity that'll be rotational, and I'll do this. I just assume kind of move backwards. Okay, so mass is a scalar quantity because mass is just how much of you there is, right? The more matter you possess, the more mass you have. Are your mass and your weight the same thing? Okay, we talked about that before. It's important to recognize that. Okay, weight is the force of gravity pulling on your mass. Okay, mass is how much of you there is. Okay, and it's always there. Okay, so you have to be mindful of it. Even in a zero gravity situation, you might be weightless, but you're never massless. Okay, you always still have that inertia and that mass. All right, we'll talk more about that tomorrow. Okay, got a couple more videos, got some smart cars getting destroyed. Okay, that I'll show you tomorrow.